Hey everyone, welcome back to the channel. Today we are breaking down how to actually test cryptographic controls, the encryption and the key management controls that sit underneath almost every compliance framework you have heard of. We'll walk through this using a real world setup, Azure Key Vault on one side and on-prem PKI environment on the other. By the end of this video, you'll have a complete audit-ready workpaper template you can reuse on your next engagement. Quick reminder, this channel is brought to you by Audit.site. So if you're studying for a certification or building out your audit program, check the link in the description. Stage 1, control mapping across standards. Let's start with why this control matters so much. Cryptographic controls aren't just one line item in one framework. They show up everywhere. ISO 27002 covers it under A10 cryptography. SOC 2 calls it out in CC 6.7. PCI DSS has it as requirement 3, protecting stored cardholder data. GDPR and India's DPDP law both require it under Article 32, and NIST CSF splits it across PRDS2 and PRDS5 for data at rest and in transit. Here's the key takeaway. If you test this control once thoroughly, you can map that single test to 5 different frameworks. That's a hugely efficiency win if you're running a multi-framework audit program. Before we get into the testing steps, let's talk about what your actual workpaper needs to contain. Every single control workpaper you build should have these 9 sections in this order. The control objective, your control steps split into design and operating effectiveness, your sampling strategy, and we'll cover why 5 is the minimum, the evidence required, a step-by-step testing procedure, 8 design effectiveness checkpoints, 8 operating effectiveness checkpoints, your results comparing expected versus actual, and finally your conclusion and recommendations. Keep the structure on a template, else it will save you hours every single engagement. Now let's zoom out and look at the full methodology from start to finish. 10 stages. First, planning. You define your scope, which is cryptographic controls across Key Vault and on-prem PKI. You identify your criteria across all 5 frameworks. Second, evidence collection. Logs, screenshots, and configs. Third, testing techniques. Inquiry, observation, inspection, and reperformance, which we'll unpack in a minute. Fourth, sampling. At least 5 keys or certificates. Fifth, control steps. Design versus operating effectiveness. Sixth, actual evidence collection steps, the clicks and commands. Seventh, test execution, comparing with what you expected to see against what you actually found. Eighth, documentation. Ninth, findings, write-ups for anything that didn't pass. And 10th, your conclusion, where you rate the control's effectiveness and tie it back to the frameworks. Let's go through each of these in more depth. Evidence collection. Evidence collection splits cleanly into 2 lanes because you've got 2 environments. On the Azure side, you're going to export the key rotation logs directly from Key Vault. Grab a screenshot of the certificate expiry alerts from Security Center and screenshot the encryption settings to confirm customer managed keys are actually turned on. On the on-prem side, you're exporting the certificate store using certificate-manager.msc, running a PowerShell script to check key rotation and pulling the encryption policy document itself. Same control to completely different evidence trails, and you need both to call this testing complete. Testing techniques. There are 4 testing techniques you will rely on, and honestly, these 4 apply to almost any control you test, not just crypto. Inquiry means literally asking the admin team how keys are getting rotated. Get into their own words. Observation means watching the certificate renewal process happen in real time, not just reading about it. Inspection is reviewing the actual logs and config files after the fact. And pre-performance is the strongest one. You actually attempt to encrypt and decrypt test data using the current keys yourself to prove the control works, not just that someone says it works. Sampling strategy. For sampling, your minimum is 5 keys or certificates, and I want to stress the word minimum, not a hard cap. But don't just grab 5 active ones and call it a day. You want a deliberate mix, 2 active, 2 expired, and 1 revoked. That mix is actually what stress tests the lifecycle management process, not just the happy path. And just as important, make sure your sample spans both environments. If all 5 come from Azure and none from on-prem, you haven't actually tested the on-prem PKI process at all. Control steps. Design effectiveness versus operating effectiveness. Every control gets tested twice conceptually. First, design effectiveness. Is the control designed correctly in the first place? That means the checking that policies, lifecycle definitions, and storage design are actually documented and adequate. Second, operating effectiveness. Did the control actually run the way it was designed to throughout the period? That's where you're pulling real logs, real expiry alerts, real rotation evidence. A control can look great on paper and still failing to operate effectively if nobody is actually following the process. Its collection steps. Let's get really specific because this is the part people usually mess up. The exact click path. In the Azure portal, key vault, then keys, then rotation history, then export. In Azure Security Center, certificates, then expiry alerts, then screenshotted. On-prem, you're opening certificate manager.msc and exporting the certificate list. And in PowerShell, you're running get child item space cert colon backslash local machine backslash my and capturing that output as your evidence. Write these exact steps into your work paper so anyone on your team can reproduce a test. Test execution, expected versus actual. Now you actually run the test against your 5 samples. Your expected result, every key rotated within 90 days, every certificate renewed before expiry, everything stored in a HSM or KMS. In our example here, the actual result came back a little different. 2 of the 5 sample keys were not rotated within the policy. That gap between expected and actual is exactly what drives your finding in the next section. Documentations and findings. When you write up a finding, it needs 5 parts and skipping any one of them makes the finding weak. Condition, what did you actually find? 2 keys not rotated. Criteria, what standard says this should happen? ISO 27002 A10 requires periodic rotation. Cause, why did it happen? In this case, the manual process got delayed. Consequence of what? There's a risk of key compromise and recommendation. What should they do about it? Automate the rotation process. Condition, criteria, cause, consequence, recommendation. Memorize that order is the backbone of every audit finding you'll ever write. Design effectiveness checkpoints. Here are your 8 design effectiveness checkpoints. Basically, your pre-flight checklist before you even test operations are encryption standards documented, like AES 256 and RSA 2048. Is the key lifecycle defined? Creation, rotation, destruction. Are encryption requirements documented for both data at rest and in transit? Is there a defined certificate management process? Is key storage designed around an HSM or KMS? Is there a documented crypto incident response plan? Is access controls for keys clearly defined? And are crypto logging requirements documented? If any of these 8 are missing, that's a design gap. And it doesn't matter how well the control operates day to day, the design itself is incomplete. Operating effectiveness checkpoints. And here's the operating side, the same 8 ideas, but now you're confirming they actually happened in practice. Encryption at rest enabled, TLS 1.2 or higher enforced, key rotation actually performed, certificates renewed before they expired, keys actually stored in the HSM or KMS, key access logs actually reviewed, crypto alerts actually monitored, and crypto incidents actually logged. Notice the pattern, every design checkpoint has a matching operating checkpoint. That's not a coincidence, that's the whole point of splitting design from operation.